To start, let me talk about the analysis of multipartite entanglement distribution using a central quantum network node. It's quite a mouthful, and I'm not going to be going into too many details of the analysis itself. Mostly, I want to use this paper as a way of discussing what multipartite entanglement is, and some ways that they analyze of how we can actually go about distributing multipartite entanglement within a network setting. So to start, let's think just in terms of of normal bipartite entanglement where we have two parties involved, like Alice and Bob, as usual. We know this case quite well. It's what most of quantum networking is sort of working towards right now, is trying to get two parties entangled upon request in a dynamical and efficient fashion. Because it's very useful, right, to have a Bell state between Alice and Bob. It's a resource that they can use. It's interesting though, because once you have more than two parties, once you have say three or more parties, the kinds of entanglement that you can actually generate and use kind of expand rapidly. So for bipartite entanglement, n equals 2, you just have one type of entanglement. We have different Bell states, but they are all of the same type because they can each be transformed into each other just by one of the parties doing something on their own. It doesn't require sort of more entanglement to change a Bell state into another one. And so that's why when we're talking about entanglement, we say we want this many Bell states, because that's the sort of or EPR pairs. It's often called, because that is sort of a definite amount of entanglement that we can say. When we get to more than two parties, like three, which I'll mostly be focusing on here, there are now more than one different types of entanglement, in the sense that one type of entanglement cannot be transformed into another one just by the local parties doing things locally. So for three parties, for tripartite entanglement, as it's called, there are two types of states: the GHZ states and the W states. And you can see on the slide here what their canonical form looks like. So in this paper, we'll kind of be focusing more on the GHZ state, which, as you can see here, is a superposition of say three parties being in an entanglement state of 0, 0, 0 plus 1, 1, 1. So like a prototypical Bell state can be 0, 0 plus 1, 1, right? And that means that Alice and Bob, if they have those two qubits, are entangled. If Alice, Bob, and Charlie have three qubits that are in the entangled state 0, 0, 0 plus 1, 1, i.e., if one is 0, they will all be measured to be 0, and vice versa. That is a GHZ state. And as you get to more parties than that, the space of different types of entanglement explodes. So let's just focus on three parties for now. But the takeaway is that there are sort of more complicated forms of entanglement than just the usual two-party entanglement that we're used to, and they have different applications. They can be used for other things that the usual two-party entanglement can't. And so what this paper basically does is look at, okay, we know that multipartite entanglement is useful. For example, the GHZ state can be used for and the applications that they have specifically are still sort of being researched, but there's quite a few different applications that have been sort of discovered and played with in regards to these types of multipartite states. So, but the question is, how do we actually get them to where they're supposed to go, right? The usual distribution problem. So that's what this paper talks about. As a preamble, let's remember first how we distribute normal bipartite entanglement usually in a network setting, right? And the usual picture that we have is of n nodes that are able to establish entanglement with some sort of central node, and the central node here being a repeater will do a Bell state measurement or a BSM, which is the same thing as swapping the entanglement. And in this way, the two entanglements get tied together and become one longer entanglement, right? One thing to note here is that this is actually just the same as teleporting one of the entangled qubits in the central node along the chain. It is the same thing. So whether or not you're saying swaps or BSMs or teleportation, they're all basically the same thing. And that's where we start with with repeaters and entanglement networks. Once we get to 3 parties or more, right? You can do the same basic idea. You can have a central node and have each party establish entanglement, normal bipartite entanglement with the central node. And then what the central node has to do is that instead of performing a Bell state measurement, it performs a GHZ state measurement, which can always just be done via some form of interference between the photons that are the qubits, followed by a measurement. And when you do this, you can distribute whatever state you're able to do the measurement of. And the advantages of this are as I said, it's easy. You can do it with normal optics. And if you don't have a memory, of course, then the problem is though that you need to have each photon arrive at the same time, which can be tricky sometimes. As well, if a single photon is lost along the way, then that ruins the attempt for everyone, right? So this is kind of the prototypical, say, 3-party repeater, or sometimes called a switch. And what this paper does is it basically looks at this type of central node, but assumes that we have access to quantum memories that can store the qubits until basically all of the qubits are ready for the measurement to happen. And so that is what is what they refer to in this paper as a factory node or an end switch. And again, it requires memories, and so you kind of have this picture as we see in these in this diagram, where as usual, each end node establishes a Bell state with the central node. The central node, once all of those qubits are in place and in memory waiting, is able to then generate whatever state wants to be distributed. In this case, a GHZ state in this image. And then we simply teleport each of those qubits to their respective end nodes. I.e., we do 3 Bell state measurements in this way as in the figure, and you're able to sort of teleport whatever state you generate in the central node to the end nodes. And so that's kind of one of the models of a central node that they look at in this paper, and the one that they kind of focus on more. In this image, they are distributing they are generating and distributing a GHZ state. But of course, in principle, this can be done with any sort of complicated n-party multipartite entangled state, as long as you can generate the state and then teleport each of those qubits to the end nodes via a BSM. Then you can do that. In the paper, the analysis that they did was restricted to just GHZ states, but in principle, it can be used for any state. This can kind of equivalently be thought of in the same way as before, where we have sort of a generalized measurement happening. The key difference is that we have memories that are in place, so that each link can kind of establish elementary entanglement independently of each other. And so yeah, I just wanted to mention that it may be easier to generate the required state. It may be easier to do the corresponding measurement. So whatever way is easiest for your hardware, the kind of idea is the same. I just wanted to mention that. So that is scheme 1, as I'll call it, the factory node. The other basic way of doing this that they analyze in this paper also assumes that you have a memory in your central node, but it's a simpler central node. In this case, what they call a 2-switch. It's basically just a repeater with access to memories, so that each of the two sides of entanglement can be established independently and don't have to arrive at the same time. So in the 2-switch, what happens is that the switch acts as a repeater for establishing a Bell state between, say, Alice and Bob, and then does the same thing between, say, Alice and Charlie. And then at that point, Alice has 2 qubits that are each entangled with a different party, and she can actually then do what's called a fusion operation to transform the state globally into a GHZ state. So kind of a fancy way of doing it here. The disadvantage of this, the advantage is that the two switch is simpler. It only needs to be able to store 2 qubits and do BSMs, and that's it. The downsides are that it therefore requires a bit more of the end nodes themselves, right? So here, the end nodes actually have to be able to store more than 1 qubit and do this fusion operation, which is a 2 qubit entanglement operation. And so that's a bit more than just holding a qubit as before. And the other downside is that not all multipartite entanglement states can be reached by this method. A GHZ state can, but not all can. So depending on what you want to do, this may not work for you. So that hopefully gives you sort of a flavor of the dynamicism that we can kind of that becomes at play in regards to how we actually think about distributing entanglement and the ways that we can do it. In this paper, they actually go through like a whole simulation, and they simulate the performance of both the factory node and the two switch, and they look at at the fidelity and the rate at which they can actually get GHZ states to the end nodes. I'm putting the images, the figures in the paper here just so you can see them and maybe pause if you're watching later. But the basic takeaways are from their analysis is that it really depends on the specifics of your network, as with most quantum networking, right? So what they take away from their analysis is that the factory node is in general more resilient to noise in the links that establish elementary entanglement, and to noise in the memories themselves in the central node. On the other hand, the two switch has, aside from being the two switch has its own advantages and disadvantages that I already mentioned. Beyond that, in the context of the analysis, the two switch is better than the factory node if the BSMs are probabilistic or noisy. So if you have if you're able to do sort of perfect teleportation, perfect Bell state measurements, then the factory node might be better. But if your BSMs are sort of a little bit wishy-washy, then the two switch is better at that. Is better at handling that noise, and it's also better at in general with its scaling with the number of nodes. So it can service a greater number of nodes in the end, and also has a rate advantage in general over the factory node. So I think that this actually was the opposite of what the authors expected. They kind of expected the more complicated factory node to be overall better, and in some cases it is, but it generally depends. So I hope this kind of just gives you a sense of how we're thinking right now about how we can actually get entanglement to where it's supposed to be, and the best ways of actually doing this in the future.